Hello and welcome to Dr. T's Math. In this video, I'm going to look at some possible A-level exam questions. Now, I've been in education for a lot of years, and I've been teaching math for a lot of years in a lot of different countries. And to me, math is just math. Of course, there's different ways to assess learning. And of course, some tests have multiple choice and others have constructed response. But there is some sort of idea in education that a different country's curriculum is so different from my home country or from another country's, maybe in some subjects. But when it comes to math, I mean, we're still doing math. There are only so many different ways you can do it. That's kind of the whole idea of math, that it's international and that we can have different people in different countries come to the same exact solution given our common language of math. And so the idea that British curriculum and American curriculum and IB and all of these things are just so impossible to understand unless you have some specific certification is kind of silly to me. But aren't people just so proud of their culture and so proud of their standards? And it's hard to tell anybody just about anything these days. And so sure enough, there are those who believe that British curriculum is just nearly impossible for somebody to understand unless they're certified or unless they have experience in British curriculum. And aren't the Brits so proud of everything that they do? But anyway, I digress. We're here to do math. So let's look at some sample A-levels exam questions with regard to trigonometry. And you might notice that basically this is just the quadratic formula, this type of question. And why they can't use technology on these exams, I certainly don't know. Technology is here to stay, but don't the Brits just love to have their 17th, 18th, 19th, and 20th century mindsets, because those were the peak years for the British Empire. So let's just humor the Brits, since they can't do any better. They know no different. They can't use a simple calculator and graphing utility on exams. They can't allow accommodations to anybody because they're living in the 17th century or something like that, or maybe the 20th century. So let us just humor them and let them think that they're normal, rational people when assessing student learning in the 21st century, where technology is not going anywhere, and AI is going to soon be able to calculate all of our algebraic stuff here. So what you might notice is that this is the Pythagorean identity. And since we've got cosine on that side, what we're going to do is try to get cosine on both sides. And so since sine squared x is equal to 1 minus cosine squared x, we're just going to substitute there, and that's still equal to 12 cosine x. And we're going to distribute. We'll get 3 minus 3 cosine squared x is equal to 12 cosine x. And then we're just going to treat this like it's a quadratic since we have a squared. We're going to act like cosine x is just x, or you could substitute any other variable as you like. And we're going to move that to the other side in order to get the leading coefficient positive. So what we're going to end up with, I'm going to skip a step here, is 3x squared plus 12x minus 3. And you can see this is a standard quadratic equation. This is, like, again, trickery. Oh, those wacky Brits, aren't they really assessing learning? No, somebody could go through this algebra and still not know what the heck they're doing or how it applies in the real world, but never mind. Let's just have a bunch of pencil-pushing introverts who can calculate things to the nth degree, but you might have noticed that I have slight hostility toward disconnected thinking and ethnocentric thinking and thinking that is, in my opinion, beyond the boundaries of rational reality in the 21st century, especially with regard to math, when almost nobody likes doing it, almost nobody can understand what's going on with regard to it, and almost nobody has the patience to just sit around and plunk away at calculations all their days and nights. But let's just apply the let's apply the quadratic formula. Since here we're going to get 3 and 1, here we're going to get 3 and 1, and there's no combination of 3 times 3 or 3 times 1 that's going to give us 12, so we got to use the quadratic formula. So we're going to get b squared is 144 minus 4ac. 4 times a times c is going to turn that positive. 144 plus 36. 3 times 4 times 4 is 9 times 4, or 36, and that's going to be divided by 2a, which is 6. And we'll just keep going on that path. We're going to get the first part here, negative 12 divided by 6 is negative 2. And we'll have plus or minus 144 plus 6 is 150. 150 plus 30 is 180. That's going to be divided by 6. We're going to carry that out. Do some things with our rationals here, or sorry, our radicals here. We're going to have plus or minus. 180 can be split up into its parts. 180 can be split up into 36, which is a perfect square, times 5. And then we'll break down that perfect square by taking the root out. We're going to get 6. 6 is the square root of 36, and then that little root 5 is going to be kept over there, divided by 6. Those cancel out. So we got negative 2 plus or minus the square root of 5. Whoopity-doo, what does it all mean? Well, we're going to take that now and put it into an inverse cosine or an arc cosine function. So the inverse cosine of negative 2, we're going to try plus or minus root 5, but I think we're going to stall out on the minus root 5. And this is where we do need a calculator. It's just that, you know, my first thought when looking at this thing is we just type it directly into a graphing utility. Bang, we're done. 3 sine squared x is equal to 12 cosine x, and we're going to get some solutions here. 1.33, we're usually dealing with between 0 and 2 pi, so we got 2 solutions there, 1.33, 4.95. But no, we're not allowed to do that. Not in British curriculum. In fact, I will need a scientific calculator here, or it's going to be a lot simpler. So let's look at this one, CAS calculator, or there, psi calculator. That's going to be the better one. Let's try inverse cosine. Where are we? Inverse cosine. Inverse cosine of negative 2 plus the square root plus the square root of 5. Gives us 76, and we're just going to keep that in mind, 76.35. Now let's try the same thing, inverse cosine, negative 2 minus the square root of 5, undefined. Yeah, and that's going to be because, let's look at that value, negative 2 minus the square root of 5 is negative 4.23, negative 4.23. And let's just play around with a couple values here, right? Let's play around a little bit. Let's try negative 3. Undefined. How about inverse cosine negative 1? Well, that gives us a value, but negative 3 doesn't. Well, let's try another one. Let's do inverse cosine negative 2. Undefined. Well, let's try just less than negative 2. Just less than negative 2. Negative 1.99. Still undefined. About negative 1.5. Still undefined. And so it's only going up to 180 degrees. And anything beyond that is not going to be defined. So let's take that at face value. Coming back here, though, let's look at, this is negative 4.95, which is not the same as negative 4.23. So let's just stick with this 76.34, 76.34. Going back to our original question, 76.34 is our value. So we got 76.34 degrees. And if we recall, 76.345, we'll call it 76.35. 76.35 degrees. And let's look at a new page for our unit circle. 76.35 degrees is going to come somewhere in here. 76.35 degrees. And if we've got, remember, all students take calculus, where our x value is going to be our cosine. And so whatever this x value is here, it's positive. All of the signs, all of the functions are positive in the first quadrant. This cosine is positive in the first and the fourth quadrant. So we're going to have another value here, another value down here, which is the same reference angle. The reference angle is this angle that it makes with the x-axis, and so those two are equal. And so this is going to be at negative 76.35 degrees. And 360 minus 76.35. Calculators are here to stay, in part because they're right every time and they're faster. 360 minus 76.35, 283.65 degrees, 283.65 degrees. Now let's see if 283.65 is that 4.95. And to do that, we got to convert between radians and degrees. 283.65. 283.65 degrees. So those are our two values. Now let's look at converting between degrees and radians, because GeoGebra is going to give us radians. We're going to take 76.35, divide it by 360, because that's the ratio out of one full circle circumference that that angle makes. And that's going to be equal to something over 2 pi. So what we're going to do is first divide 76.35 by 360. 76.35, let's actually, can we copy that? Can I copy that? Nope, can't copy that. 76.35 divided by 360, 0.212. Now we're going to multiply that by 2 pi. And what do we get? Okay. Answer, can I insert the answer? There we are. Answer times 2 pi, 1.33. And that 1.33, well, again, calculators and technology faster, but aren't we still living in the 20th century where your teacher would tell you, you're not always going to have a calculator in your pocket? No, everybody's got all the books that ever written in their pocket. 1.33, so these match up. And so all we're doing now, the calculator has been relegated to the checker, and we just have to spend our time plunking around with the details that the technology is faster and more accurate with, but can't try tell that to somebody whose entire life's work has been made on making people terrified of some exam that they have to sit. Next one, 283.65. 283.65 divided by 360 gives us that. Insert our answer, multiply it by 2 pi. Oh, and lo and behold, we get 4.95, making sense of the graph. And so I always like to say that graphs and tables and algebra are just three sides of the same coin. I don't think we should have to prove it in every instance, but there we took 10 minutes to solve a 2-minute problem. Let's try one more, since we have time for one more. Those British A-level head teachers and such would be so proud of you if you could never use a calculator and you could just sit and spend your hours and hours and your days just writing out little algebraic equations, and you never need any of those nasty American technological implements of British demise. No, all you need is your abacus, or all you need is a mind, and you can solve all of the problems in the world. Well, false, obviously, but I'll try to tell that to somebody who's not paying attention anyway. All right, so we just substituted again. This is just strategic application of the Pythagorean identity. And I suspect people are, the testers are just trying to assess whether people know where to substitute. Substitution shows up many times in algebra, many times in mathematics, and sometimes it can get kind of confusing for students. So on the one hand, I get it, why this is this way. On the other hand, I really don't get what they're trying to accomplish here. 3 sine x plus, we're going to change the sign here, plus 1 sine squared x. And then plus, here's our middle term, 7 sine x. And we're going to change the sign. Plus 4 is equal to 0. Oh, not plus 4, excuse me. Plus 3, because we got to combine the 1 and the 4. And so we're going to have plus 3 there. Plus 3, change the sign. 1 minus 4 is negative 3, change the sign when we move it across the equal sign. And there we are. And we're on our way to being little Ibn al-Haythams. Right? So we got combined like terms, plus 7 sine x plus 3 equals 0. And then we're just going to do that fancy schmancy substitution technique that I guess isn't entirely intuitive, but it once you figure it out, it is. It's not exactly the first thought that crosses my mind at this stage. If I'm out in the working world, do you really think that anybody out in the working world is paying attention to all of these little calculations? And do you really think that they would waste their time rather than use a calculator? Obviously not. Of course, it is important to understand what's going on here, and it's hit and miss with kids. It's hit and miss. And how do you, at scale, how do you assess that a student is learning when there are so many ways to make it look like they're learning, but they're not? So there are good reasons and also not good reasons why they do the testing like this and why they do education like that. Well, 12 plus 1 is not going to work out. What we're looking for here is we're going to get in something plus and something plus, because we've got plus plus in the parentheses, then it'll be plus plus. 12 and 1 gives us 13. That's not going to work. Let's try. Well, I want to demonstrate that that's going to give us the right answer. But let's look over here for a moment. 3 gives us 6. 2, 6 and 2 is 8. 2 again, 6 again. So that gives us 8 either way. 8 is not the same as 7. We're looking for 7. Here we're going to get 4 and 3. 4 and 3 together is 7, and so that's the one we're looking for. We're going to get 4 multiplied by 1, and that's going to be x. 3 multiplied by, 1x multiplied by 3. And so those are our two factored forms, and we could then check that. 4x squared plus 4x plus 3x gives us 7x, plus 3 gives us 3, and that checks out. So 4x is equal to negative 3, x is equal to negative 3/4, and 1x is equal to negative 1, and we don't have to go any further with that. 1x is equal to negative 1, and so let's put that into, the calculator again. Well, we need a calculator, but not that kind of calculator. Aren't those Brits just a hoot? I feel like I'm living in the mid-20th century. You got your TI 002 calculator. 4 functions. Four functions. Where are we? So we got negative 3/4 and negative 1, and we're looking at inverse sine of negative 3/4. Keep that in mind, and inverse sine of negative 1, of course, is going to give us negative 90. Negative 40.59, call it negative 40.6, and negative 90. Now let's open up a new window. Recall those values. Negative 48.6, I believe it was, negative 48.6, and negative 90, and negative 90. And let's draw ourselves a unit circle. Now we could, again, just through rote memorization, recall these things, but is it really all that important? Nobody's actually spending time doing this stuff in the real world, and so what does it matter if you spend a little bit more time on some tests? We're going to have plus and minus. Minus 48. Oops, we're in sine now. Excuse me. The last one, the previous one was cosine. So we're at negative, still the same angles. Negative 48. And it's not going to work out in the same quadrant, though, is it? Right? So let's get rid of that. The previous example was cosine, so cosine is positive in the first and fourth, but remember, all students take calculus. Sine is positive in the first and second because sine is the y-axis. Sine is the y-axis here. And so we're going to get negative 48. See? I guess that we could speed things up a little bit by just memorizing. But we're going to get the angle of reference is negative 48.6, and then again negative 48.6. But it's going to be, in this case, 180 plus 48.6, because our reference angles here are the same. So 180 plus 48.6 is 228.6 degrees. And whoopity-doo, what does it all mean? It seems pretty detached from anything functional. I mean, these are the foundational stages. Let's just do this one let's do the other one here, just for good measure. So we've got our unit circle, we're at negative 90. Here's our unit circle, we're at negative 90. Well, it's just going to be directly across. Negative 90, positive 90. But let's just look ahead anyway. Let's skip ahead a little bit. I'm just really not. I'm not all that into what the Brits think is the tip top of everything. So let's just look at 3 sine squared x plus x plus 7 sine x, and that's going to be equal to, remember our original statement here was cosine squared x minus 4, and we're going to get 3.89 and 5.43. 3.89, 5.43. Again, we're usually interested in between 0 and 360 degrees, or 0 and 2 pi. Now let's take those values there, negative 48.6, 228.6, and see if we can make sense out of the graph. So negative 48.6 is in fact a positive number. We're going to have to say 360 minus 48.6, and then we're going to divide that by 360. Back to the calculator. 360 minus 48.6 gives us 311.4. We're going to divide that into 360. Get 0.865. We're going to multiply that by 2 pi, and 2.71, 2.72, 2.71. That is not on the list here. Let's see, cosine squared minus 4, 7 sine. Let's look at the other one. 228.6, 228.6. Oops, wrong one. 228.6 divided by 360. 0.635, and then again we're just converting to radians, times 2 pi. Answer times 2 pi. 3.98, 3.98. And that's this one here, 3.98, and then 5.43. Let's just go back and make sure everything is spick and span. Negative 48.6, that's this number of degrees here. Let's go back and Oh, I multiply this by pi, look at that, times 2 pi, 5.43. That's where it's at. 5.43. So the more steps and the more human stuff that goes on here, the less likely everything is to work out. All right, so let's look at sine 90. That's not even listed. You might have noticed it's not even listed on this here. So instead of that, let's try, we got two values. Let's just pretend like everything is correct. And how can we make this work out? Let's try 4 sine squared x plus 7 sine x plus 3 equals y. And there we are, 0, 3. Those are our roots. 0, 3. Now, what happens to the y? Let's go back over here, and we're going to get sine of 90. What happens to sine of 90 and sine of negative 90? Negative 1. Oops. Only one value there, my fault. Only one. Obviously, this is negative 1. That's positive 1 on the y. Obviously, right? Obviously. So negative 90 is only here. We don't have a second angle that's going to equal negative 1, right? There's only one possible angle, and it comes from both sides of the y-axis there, both 90 degrees. It's negative 90 over here, and then using the same rule, our reference angle is the same. And then positive 90 from the 180 gives us the same negative value of y. And so the real question is, why doesn't it show on this graph? But it does show on this graph as the y-intercept at 0 and 3. That be the question. All right, so maybe we just discovered one small error in using technology. Now, I'm sure there's another way that I could reference this. Let's look at bring over the cosine squared and the 4 from the start. Y equals 3 sine squared x plus 7 sine x minus cosine squared x plus 4. That's going to be the same thing. Course, of course. And what are we really looking for? Y-intercept. And it's going to be this one right here. No? No? It's going to be that right there. Roots from function is that. Function is, say, g from 4.4 to 5, and it's not going to give us anything. But we can see, let's look at 90. Negative 90 is going to be 270 degrees. 270 divided by 360 is 0.75. 0.75 times 2 pi is 4.71. And in fact, that is that value right there, is it not? 4.71. Now let's take and see what we can do here. All right, so the Brits redeem themselves, if only just ever so slightly. Let me see if I can. 0.75 times 2 pi, 2 times 0.72 times 0.75 is 1.5, so 3 pi over 2, obviously. That's where we are here, 3 pi over 2. And let's just find the g of 3 pi divided by 2 is 0. See, and there's the problem with, that's GeoGebra, really. That's not the graphing utility, just what graphing utility. So I don't know. It's arguable. It's definitely arguable. So by looking at this graph, we're looking for solutions. There are the solutions, and GeoGebra just doesn't really interpret that as a root because it's like a double root, or it grazes the x-axis and comes back down. But if I type in g of 3 pi over 2, it gives me 0, showing that it's a root. And so the Brits are hanging on by a thread with this A-level stuff here. But anyway, indeed, it's good to be able to pass tests, and it's good to be able to do good on tests. I just got to question why we got to spend a half hour to do something that should take like 2 minutes, especially in 2024. But this has been Dr. T's at Math, and thanks for watching if you did.